Hey, so as I emailed you the midterm exams, the booklets are out in the hall out here on the second floor in literature racks. Just look for them on the wall. And I posted both the exam and solutions to the exam on the class website in the resources. What else? Any questions, issues? Okay. Where we left off last time is in looking at flashlights is how the battery provides power to the current in the wires, in the circuit as a whole, and how the filament then receives that power and turns it into thermal energy and ultimately into light. Just try to make sure that I made all that clear and sort of convey it as well as I can. I'm going to sort of revisit and circle that around. I edited this particular slide to include the concept of a voltage drop in it on the fifth line, I guess. Let me find my... So to review the idea of a flashlight circuit, sort of disassembled in the case of this thing I've got up here, the battery's job, first off, it is a circuit. It is a racetrack for electric charge. Has no beginning or end once it's active. Once the switch is on, it's a continuous circuit for good reason. The battery's job in this circuit is to take the passing electric charge and add energy to each charge. Adding energy to each charge, energy per charge, means increasing its voltage. Yay! So the battery's job is to add energy per charge. And this particular battery adds 12 joules to every coulomb that passes through it. So it's a 12-volt battery. It takes charge at 1 voltage, at a low voltage, and delivers it at a high voltage, 12 volts higher. I go back occasionally to this notion that I can't be certain what exact voltages on these various wires, and I guess that may be me being obsessive. But the fact is, if I have to know exactly what the net charge is on this entire thing to know what the absolute voltages are on that. Like if there's a lot of excess positive charge, then this whole thing is probably up a little bit of positive voltage relative to infinity, the distant stars. On the other hand, if it's got a lot of excess negative charge, it's at negative voltage relative to the star. That typically doesn't matter. In most situations, you don't really care about absolute voltages, what the voltage of a particular location is relative to the stars. Instead, you care about differences in voltage, because they tell you how much energy is added or subtracted from the passing charge. Is that okay? The idea that absolute voltages don't matter a whole lot in most situations. So I can just like pretend I know the value. I can pretend this is 0 volts here at the negative terminal of the battery, that it's truly 0. And the job of the battery then is to take charges, and again, charges without any modifier in front of it, they are positive charges. It takes positive charges from the 0 volt terminal here and chemically pumps them against their will onto the positive terminal of the battery, which is 12 volts higher in voltage. And that means it's got a lot more positive charges piled up there. And the battery has to do work on the charges to shove them, to tear them away from the negative terminal and pile them up on the positive terminal. That's an action that requires work. And the battery does work on the charges. It does 12 joules of work on every coulomb of charge that goes through it. That's 12 volts. Is that okay? So there is a voltage rise. I'll go back to the previous slide, even though I did it last. The battery's job here is to use its chemical potential energy to create electrostatic potential energy, transform it into electrostatic potential energy. It creates a voltage rise for the current. The current arrives, and again, current is charge per time. And I'll come back to that and make sure that, do my best to make sure that's clear too. So as charge flows through this battery from the low voltage terminal to the high voltage terminal, propelled by the battery's chemicals, the current experiences a rise in voltage, or a voltage rise of 12 volts. And to illustrate this, if I ask you all, are you visual learners? Pretty much everyone will say they're visual learners. So I'm going back to a demonstration I haven't used for, 10 years. Pretend these little trucks are charges. And the trucks drive around the circuit. They leave the positive terminal. They go through the switch when it's closed. They go through the light bulb, and they return to the battery to be pumped again by the battery. So these are the charges, and I got 3 of them at the moment. When they go through the battery, I realize this is kind of, I don't mean to be patronizing or whatever, but I'll do it anyway. Going through the battery, they pick up energy, right? Ghirardelli. They pick up energy. That's the voltage rise. They're picking up energy. They go through the circuit, through the switch. Oops, they dropped off their energy early. Come back. Get your energy back. When they reach the filament, the goal is to have the energy dropped off so the charges shift from high voltage, 12 volts, to low voltage, 0 volts. The charges go back, and they pick up more. So the charges go around and around. The purpose of this arrangement, battery, wires, light bulb, is not to deliver charge. The battery is not, you don't want to take charge out of the battery and pile it up in the light bulb. That serves no purpose. And furthermore, it's going to be hard to do because when charge accumulates, it hates being together. So electric circuits, which is what this is now, their purpose is not to deliver charge. Their purpose is to deliver energy by way of moving charge. The charge goes round and round and round, gets reused. So it's different from water delivery. In water delivery, you actually take water that was started at the water company or a lake, and you deliver it to some household. And they actually want it there. They might fill a pot with it. Electric power distribution in general doesn't try to deliver charge. It tries to deliver power, which is related to energy. And so you don't keep the charges. They might arrive packed full of energy. You take the energy from them and send the charges back to go get more energy and come back again later. You see the difference? So that's ultimately the reason behind circuits. The circuits always involve, at a minimum, 2 wires. 1 wire to deliver the charges, all packed full of energy, and therefore at positive voltage, and a 2nd wire to receive the charges back. If you're receiving, being like the battery receives charges back through the 2nd wire. They're barely making it home. They're almost out of energy, but they get back to the battery. The battery shoves energy into them, sends them off to do their work again. 2 wires. This is why circuits, often if you touch only 1 wire in some electric situation, you're usually pretty safe. Not much bad is going to happen because the charge comes onto you, but it has nowhere to go. It may deliver energy once, but no more charge will join it because it's now repelling any further charge. If you touch 2 points within some electrical arrangement, now you're vulnerable to trouble because the charge can arrive through the high voltage side, drop off its energy, and leave through the low voltage side. Suddenly you become a consumer of electric power, and that may not be so good for you. All right? Questions about the circuit idea? All right. So the battery the battery produces a voltage rise for the current. The current goes up in energy per charge, and the filament's job is to do the reverse. The current going through it experiences a drop in voltage drop. The energy is being left behind in the filament. And the filament being a very simple device, that energy becomes thermal energy. The filament gets hot, so hot that it begins to emit light. That's the magic behind an electric circuit. Any questions about the ideas at this point? All right. Well, do I have anything else I wanted to include in that part of it? Not too much. Let's see. I did talk a little bit last time about the idea of a chemical cell, although I didn't start the statement with that chemical cell. Batteries are more formally called an electrochemical cell. They involve chemicals, and they involve electricity, so they're electrochemical, and they're using a chemical reaction that consumes those chemicals, actually, and consumes energy that was invested in them during the manufacture of those chemicals to do work on electric charge. And depending on the chemistry, I told you last time, some chemistries produce very small changes in voltage, others pretty large ones. The lithium chemistries are among the, maybe they are the highest voltage difference chemistry. So a single cell, which is a single chemical reaction vessel with a place for the charges to arrive at low voltage and a place for the charges to leave at high voltage. That's an electrochemical cell. The voltage difference between arrival and departure can be as high as the mid-3s for lithium-based chemical cells, but that's about as high as, I've never heard of a cell higher than that. There may be ones, but they're probably not practical for some reason, either toxic or dangerous or who knows. Lithium cells are not so wonderful themselves, as we all know from recent trouble with lithium cells. What else? If you want larger voltage rises in a battery, you have to make it out of multiple cells, which is no problem. You simply take the charges that are departing from one cell, having been lifted up in voltage, a voltage rise, the whole voltage rise provided by the cell, and send them into the next cell at its low voltage end, where that second cell can pump them as well. And a third cell can pump them as well. So you can get battery systems of cells that give you quite a large voltage rise. For example, this battery, the car battery, consists of cells, each of which has a 2-volt voltage rise, but there are 6 of them. So you get 6 volts of rise. And when a battery, just sort of practical purposes, the batteries, they're known as lead-acid batteries. They contain lead, and they contain sulfuric acid, which is why they want you, when your battery dies, they want it back. You should not be putting those in landfill or throwing them in the backyard. They're full of not so great chemicals. When the battery, why do we use those batteries? Because they can provide an enormous amount of power in a short, at once, which is required for starting a car engine. They're able to do a lot of work on a lot of charge per second. They are also rechargeable, so that which I'll talk about shortly. So you can run them backwards. You can run the whole process backwards and reinvest chemical potential energy in them. And they'll do that many, many times until they won't. And usually what happens is some structure within one of the cells collapses. Rechargeable batteries have one simple requirement that the process of consuming the chemicals and then trying to energize the chemicals, it can't change the physical structure of the chemicals very much. You can't have, for example, the whole thing melting into soup during the consumption of energy and then hope that when you run it backwards, the soup reconstructs the original shape and size and features of the battery. Those kind of batteries are dead. You run them one way and they can't run backwards successfully. Lead-acid batteries are one of the ones that recharges nicely because the structures don't change physically in shape during the power consumption process. And so when you run them backwards, you can't really see very well that the battery is discharging, and you can't see very well that it's recharging because nothing physically changes much. But if something breaks off during the recharging or discharging process and just drops into the bottom of the pot, which is what typically happens, you lose a cell, and suddenly the battery, not only is it unable to pump charge across that one cell, but that cell is sort of out of the circuit. It's like a broken circuit. There's just nothing there. And so you may encounter may have a time when you're trying to start your car. It started fine last time, and now there's click, 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 nothing. Just gone. Or just the wimpiest little sound out of the starter motor. You may well have lost what's known as a plate from your lead-acid battery. It just broke off and just dropped into the bottom of the pot. Okay? Okay, I asked you this question last time. I'm not going to ask it again, which is the reason that power finally moves from the battery to the bulb is a statistical one, that the power starts in this beautiful ordered arrangement of chemicals in the battery. When the circuit does its magic, it consumes that power and turns it into thermal power, hot stuff. And once you've made thermal energy, I showed you it's stirring the purple and white beans. It's very hard to unstir them. So once you've shattered energy into lots of little bitties to make thermal energy, you can't unshatter it. So it's a one-way street for statistical reasons. Okay? So I got started talking about current, and I want to make sure that both power and current are comfortable for you. Again, energy is this amount. I'll start with power. Energy is this conserved quantity of nature. You can have a dose of energy, 20 joules. You're able to suddenly do things you couldn't do. You can do 20 joules of work on the world around you and get things done, maybe. If we watch a continuous delivery of energy, say 1 joule every second to the toaster. That's not enough to get much toasting done, but we'll do it. 1 joule a second, toaster gets a joule. Another second, another joule. Instead of just watching a joule all these joules, watch the rate at which they're going. How many joules per second are making this move? And in this case, it's 1 joule per second. And describing that then to someone is, you can say that this continuing process of delivery involves 1 joule per second. That is conveyance not so much of energy, but of power, energy per time. And the unit of power in the metric or SI system is the joule per second. And it's so everywhere that it's given its own name. It's called the watt. So you've heard about watts forever, right? That's what a watt is. It is a power delivery quantity. It's the unit of power delivery, and it corresponds to 1 joule delivered every second. Kilowatt hour, you should be careful. Kilowatt is a unit of power. If you have a kilowatt flowing into your house continuously for an entire hour, then you can figure out during the course of that hour, this flow delivered how much total energy? And the answer is, well, it was a kilowatt, and it operated, that's the rate at which energy came in, it operated for a whole hour, so we can figure out how much total energy was involved. It would be 1,000 watts times 3,600 seconds, that's an hour. That's 3.6 million joules arrived during that second, during that hour. Can you do that calculation? Is that okay? The rate at which energy arrived, as in power, was a kilowatt, 1,000 joules every second. Well, there were 3,600 seconds in the hour. That means that 1,000 joules arrived times 3,600 seconds. That's 3.6 million joules actually arrived overall. That's what a kilowatt hour is. So another term that you've heard your whole life. You pay for energy often in the form of kilowatt hours. What you're buying, the quantity you're buying actually then is, the unit is a 3.6 million joule unit. When I was an undergraduate, my physics professors would talk about 1 million joules was the food energy in a jelly donut, which is about right. So a kilowatt hour is about 3.6 jelly donuts. Fun fact, right? Yeah. All right. So current. I've talked about power. How about current? Current measures the delivery of charge or the amount of charge passing a location every second. Again, it's a rate. It's a rate at which something's happening. So it's a rate at which charge is passing a location. And if 1 coulomb passes this location every second, that is 1 coulomb per second of current. It's always, again, defined in terms of positive charge. So that coulomb per second, again, is so ubiquitous, at least in electrical circles, electrical engineering and stuff, that it's given its own name as well. It's called an ampere, or simply an amp for short. And so you will find, you go to the hardware store and start looking at anything electrical or gadgets and stuff, they'll tell you how many amps are involved in the current flow. Similar, it's just like they'll tell you how many watts. When you buy things, they're often rated in terms of the watts they consume in electric power and in terms of the amps that flow through them while they're operating. So just to get a sense of how much is an amp here, in this circuit I told you last time, that happens to be about 7 amperes flowing through this wire. In a lot of flashlights, it's 1 or 2 amperes flowing, give or take a little bit. Currents of hundreds of amperes rarely show up in everyday life. They show up in contexts like welding, the electric power distribution. Those are big amounts. The household appliances you plug in, usually the current flowing through those is a few amperes, something like that. All right? You okay with power? You okay with current? Any questions about either of those ones? All right. I talked also last time a little bit about the direction of current, and I'll do it one more time, and that is that because of Franklin's choice, electrons carry a negative charge, and because they're the main moving object within electric circuits, the flow of stuff in that circuit is actually the flow of a negatively charged thing. The negative charges actually accumulate here on the negative terminal of the battery. They're itching to get off because they're packed tightly there. They don't like that. They repel one another, and they're more than happy to go out on the wire, flow through the filament now, and when they go through the filament, they drop off energy. They emerge having lost a lot of energy per negative charge, so their voltage has gone up. And they then flow through the switch and back to the battery's positive terminal to be pumped again from positive high voltage to negative low voltage. Well, that story, as I just said it, is awkward. It's the flow of this negatively charged stuff. It's like negative money. I've talked about that before, flowing through an economy. It's just, it's a pain in the neck. So we just make this fiction. Just forget the negatively charged electrons and just pretend they're positively charged widgets going through. And they then leave the positive terminal. They flow down in voltage. They're pushed forward by an electric field, it turns out. The whole way, they flow through the filament. They drop off most of their energy. They go back to the negative terminal of the battery to be pumped again and go do the circuit over again. And the fact that those positive charges are fictitious makes essentially no difference. There will be contexts in which we'll have to look under the hood and notice, oh, they're negatively charged things here. But for the most part, we won't. There are situations in which positive charges actually carry current. Those are typically in things like in a solution. If you look at salt water, you look under the hood in salt water, you'll discover, oh, they're little charged, what are known as ions. They're atomic fragments floating around in the water, and all the sodium, table salt is sodium chloride. The sodium ions that are in there are positively charged. The chlorine ions are negatively charged. Well, so the movement of the positively charged sodium ions follows the rules. It's actually positive charge moving from high voltage to low voltage, given any opportunity. But not in wires, it's electrons. Sad but true. Okay? What else? All right. A little bit about how you sort of calculate power. And this I mean, hopefully will actually be useful to you at some point or other. The whole circuit, which I've got listed here in 4 parts. The first part is the battery. The second part is the wire going to the filament. The third part is going through the filament. And the fourth part is going to the battery to pick up more. So the battery, because it provides the current with a voltage rise, adds energy to the current. How much energy does it add to the current? Well, the current tells you how many charges per second are going through the battery. The voltage rise tells you how much energy each of those charges receives. So if you take the current, which is charges per second, and multiply it by the voltage rise, which is energy per charge, there's a charge in the numerator and a charge in the denominator. They cancel, and you get energy per second. That's power. That's exactly what power means. So if you want to know how much power the battery is providing to the current, all you do is multiply the current passing through the battery times the battery's voltage rise. And in terms of my silly little trucks, if you figure the current is how many trucks, 1, 2, 3, go through each second. So the more trucks, clearly the more energy they're going to pick up. And the voltage rise in the battery is how much energy 1 or 2 or maybe 3 chocolate bars each truck picks up. So if you take the number of trucks, which is like number of trucks per second, which is like current, and you take the voltage rise, which is like how many chocolate bars each truck gets, you get how many chocolate bars are being delivered every second. Trucks times chocolate bars per truck gives you chocolate bars. Okay? So that's part one, is picking up power, and that's generally true. So you'll find if you're we'll see power delivery in a household is a little different for interesting reasons, but we'll get there. But if you look at how much current you are taking from the power company, and you look at how much voltage rise the power company is giving you, typically 120 volts, that's what normal outlet voltage is. But sometimes some of your big appliances use 240 volts or even higher. Most houses don't go higher, but industry certainly does. So the bigger the voltage rise and the more current that you take from the power company, the more power is being provided to you. And that multiplication is useful. The same holds true more or less for the delivery process. If you look at the filament of the light bulb, and you want to know how much power is being consumed by that filament, you do the same multiplication. It's the current passing through the filament, that's how many charges per second in effect, times voltage drop, which is how much energy is dropped off per charge. You multiply the two, the charges cancel, and you get the energy dropped off per second, which is power consumed. Any questions about those two? I mean, I'm doing them as a calculation, but I'm hoping I'm explaining them as something that will stick a little bit. This gives you tools for actually figuring out how much power you're receiving from the power company, how much your appliances are consuming, all that kind of thing. All right. Now, why is the filament a consumer of electric power? And this is a story a little bit about the nature of electrical conductors. We'll look more deeply at electrical conductors down the road when we start looking at how, for example, an LED works. Well, metals, it turns out, are imperfect conductors. There do exist perfect conductors. I can say 2 cents about them later, but for the most part, electrical conductors don't allow charge to truly coast. In principle, if you had a perfect conductor, I'll say the perfect conductors are known as superconductors. They do exist. They are typically low temperature devices. You have to cool them quite cold. 50 years ago, the only ones that were known had to be cooled to temperatures that are essentially you can't do outside the laboratory, or they really require heroic effort to get that cold enough. When was the 80s, I guess, what are known as high temperature superconductors were invented. They still need to be pretty cold, but they're much more practical because you can cool. Liquid nitrogen is cold enough, for example, for some of these high temperature superconductors. The concept of a high temperature superconductor, what it provides for you is simple. If you put charge with energy in it at the one end of a superconductor, it will coast through that superconductor, and it will arrive at the far end with all of its energy intact. And so you can do crazy things like you can have that superconductor form a complete loop, and if you can get the charge started in the loop, it will coast. It'll coast all the way around the loop, come back, and coast through the loop again and again. And that arrangement where current is flowing forever through this loop because it truly coasts, inertia completely holds sway, those kinds of superconducting loops turn out to be useful and practical. They do exist. In fact, they're present in a number of places in Charlottesville. They are the basis for very strong magnets. We'll talk about charge and magnets down the road, but it turns out that moving currents are magnetic, and if you get one of these superconducting loops going, its magnetism just sits there trapped forever. And so if you've ever had an NMR for some sprained ankle or something like that, the magnet that you were in may well have been, in fact probably was, based on one of these superconductors. And I didn't bring superconductors in here for a demonstration, but maybe I'll do it next time. So it would be great if we had lots of those around. They're relatively impractical because they have to be cold. So what do we have? Most electrical conductors, in sort of anything we normally use, they're just metals. And just metals are not perfect conductors, which means that if you put the charge in at the beginning of a normal metal packed full of energy, it will not coast to the end with all of its energy. It will lose some en route. Why? I mean, a simplistic view of why is because as it tries to go through the metal, it actually consists of little tiny charged particles. They happen to be negatively charged, but they hit things. And they tend to lose energy. Every time they hit, they sort of lose their path. And they convert some of their energy into thermal energy. And so they don't make it all the way through. If you want an electric current to flow from the beginning of a wire to the end of a wire, you can't count on inertia. You have to push the current through the whole way. I'm going to forget that they're electrons again. The current consists of positive charges. If you want the positive charges to enter a wire and go all the way through it and come out the far end, you have to push them. Well, what pushes on a positive charge? An electric field. You need an electric field in the wire for it to carry current continuously. How do you get an electric field in the wire? Well, I told you some time back that whenever you have a gradient in the voltage, positive voltage here, negative voltage there, there's a spatial gradient in the voltage. That gradient in the voltage is an electric field. And the electric field points away from the high voltage toward the low voltage. So a little positive, this is positive, negative. I don't know why I didn't think of I always do it like this, but this is better. Hey, I invented a new way of talking through my mouth, right? On the left side of my mouth, or both sides of my mouth. So it's been a long week. It's only Wednesday. So if you've got positive voltage here, negative voltage here, you have an electric field pointing the whole way between the two. And that pushes charge forward. It would cause the charge to accelerate and go faster and faster in empty space, but the wire is not empty space. The charge doesn't continue to increase in speed, but at least it keeps going. You're kind of dragging it through the wire with the help of this electric field. So wires will carry electric current only if they have a difference in voltage between start and finish. And the current will flow from high voltage to low voltage, because that's the direction of the electric field, in the direction in which the charges are pushed the whole way. The bigger that electric field, the harder the charges are pushed, the more of them will flow per second. I'll show you that shortly. What else? So in general, wires, how shortly? Got to decide whether I want to. I'll show you pretty shortly, but so every part of the circuit, it turns out, is a consumer of electric power, except for the battery, which is a provider thereof. The filament is by far the biggest consumer of electric power. The filament is designed not only to be it's an electrical conductor, but it's a bad electrical conductor. It's one that requires a particularly aggressive push, a really strong electric field to make the charges go through it. Typically, light bulb filaments are made of tungsten wire. Tungsten wire itself is not a very good, tungsten is not a very good conductor of electricity compared to the great conductors like silver, copper, aluminum. Tungsten pretty much sucks. but it's also a very, very fine wire, often wound into a spiral, and even from the spiral, wound into a second spiral. So it's a terrible path for those poor electric charges, and they have to enter at high voltage and leave at a much lower voltage, having given up lots of their energy to struggle through the wire. So because they gave up a lot of energy in struggling through the wire, if you send any reasonable number of them through per second, which is to say any decent current, a lot of energy gets dropped off in the filament, and it gets hot. It gets hot enough that you see it. Okay? The concept of a poor conductor, of a electrical conductor that just makes the charges struggle, it's known as a resistor because it's resisting current. And different conductors have different resistances. The bigger the resistance, the harder you have to push to get charges to go through it. So if you want to get 1 ampere of charges through a high resistance, a big resistance, you have to have a big voltage drop across it to create a big electric field to shove those charges through. If you choose instead something that's a pretty good conductor, not quite perfect, but close, then you don't have to push very hard. It's got a low resistance, which sort of makes sense, and a small voltage drop is all it takes to shove 1 ampere through it. Okay? So the wires in this circuit are they are made of copper, which is as good a conductor as most people can afford. Yeah, you can go to silver, it's a little bit better, but it's like a lot more expensive. So wires are typically copper. And they carry current, but not for free. The current does not coast through them either. So it arrives from the battery at 12 volts, but by the time it has worked its way through these connections and reaches the filament, it had to be pushed forward. It will have experienced a drop in voltage, a little bit. It might not be, so 12 on entry, maybe 11.9 on exit. It lost 1/10 of a volt during its trip, because that was the toll charge, in effect, for going through the wire. When it goes through the filament, whoa, big hit. It goes through the filament and it comes out, well, it can't come out at 0 volts, because then it won't have enough voltage left to push it through the wire back to the battery. It'll come out at maybe 0.1 volt. Pretty close to 0, but not quite. It needs a little, save a little money for the last cab home. So it goes through that wire and arrives, having given it yet a little more voltage, it arrives at the back, the terminal of the battery, and gets pumped again to do the circuit a second time. Okay? Yeah, Jared. Does the charge get back to the battery at exactly 0? The voltage of that battery, which actually I chose to be 0 because I'm not quite sure, it arrives right back there at exactly 0. So the trip from here, it might be 0.1 here, a little bit of positive voltage left to push the charges by way of an electric field through the wire, and when it gets here, it arrives at the voltage of the battery, which is we defined as the 0. It really does get there at true 0. Okay. So if you look at the voltages, you label them all. And actually, there are devices that measure voltage. They go in there and they effectively play the test charge to see like what's the energy like here. And it's 0 here. It's 12 here. A little bit of a drop as we go through here. It's 11.9. Goes through the filament, huge drop in voltage. We're now down to 0.1. Last ride home to 0, and then it does it again. Okay? I'll ask this question because it's got a purpose to it. Flashlights, now the LED flashlights, they sort of spoil us on any sense of the number of cells in a battery and all that. But you have probably still seen flashlights that get longer and longer, and I have one downstairs, it's 3 cells, but they make them that are as large as 4 cells flashlights. They just get longer and longer, and it is the case that you want to buy the light bulb to match the batteries. If you have 2 cells in the battery, each of which is 1.5 volts, what is the overall voltage rise of the battery? You tell me. 2 times 1.5 volts is 3 volts. So this kind of flashlight this kind of flashlight. This has got two D batteries in it, which are chemical cells that produce a voltage rise of about 1.5 volts. It's not precisely 1.5. They list it as 1.5 because that's all they can be guaranteed. It even depends on the age of the cell. So it's about 1.5. So there are two of them, and together they will take current in at 0 volts and send it out at 3 volts, give or take a little bit. If you have 4 cells instead of 2, the voltage rise is what? 6. Yes, I heard it. I said it myself. 6 volts. 6 volts, if you apply 3 volts across a filament, the electric field is a certain amount, the current flows correspondingly, and a certain amount of power is dropped off. If you go to 6 volts from 3 volts, you push twice as hard, because the voltage drop is twice as large. So you push twice as hard, and the result is that twice as much current flows. So doubling the voltage being supplied to a filament, doubles the current flowing, and it also doubles the energy each charge drops off, because the voltage drop is bigger. That's 2 doubles, double. You double the voltage, but now you've got twice the current and twice the voltage drop. And if you remember, power delivered is the product of current times voltage drop. And each of those doubled. That's 4 times as much power being dropped off in this light bulb filament when you double the number of cells in the battery. To see whether you understood what I just said, here are the answers to choose from. This is, you double the number of cells in the battery. What's going to happen? How many think, so the choices are burn out instantly, or glow normally for a much longer time, glow normally for a shorter time, and glow for about the same. How many think it will burn out instantly? How many think it will glow normally for much longer? How many think it will glow normally for much shorter? How many think it will glow normally for about the same time? Okay, the voting's really thin. They must have busted people in or out. No, I won't go there. It will burn out just like that. And you would know this mostly if you, in the old days when you go and shop for a new light bulb for your flashlight, which is frequent. You put the wrong one in, you turn on, whoa, that was bright, but it's gone. So there's no normal about it. When the filament gets 4 times the amount of power delivered to it that it's supposed to have, it gets so hot, so fast, it's dead. It becomes basically a flash bulb. And so there were many such events way back. So you do have to match. Your flashlight filament to your cells. Actually, so this can bring me to an important public service announcement. Those of you who have traveled in Europe and have brought with you appliances from the US, particularly hair appliances. How many of you done that, plugged it in through using some plug adapter, and turned it on and had it die? Just like that, right? You did exactly the same thing. This is what you did. The power line is not quite a battery, but it's not that different. Your appliances here are meant to operate on 120 volt voltage difference, as though they were plugged into a 120 volt battery. When you went to Europe, you plugged your appliance, which is basically, these hair appliances, they're all filament based. They all have the equivalent of a filament in them as the heating element. Doesn't make light, it just gets hot. You plugged it into an outlet that delivers somewhere around 230 or 40 volts, twice the voltage. So, in your appliance, the electric field suddenly doubled, because twice the voltage drop pushes twice as hard. So the electric field doubled. Twice as much current flowed through your appliance, and because of the doubled voltage drop, it dropped off twice as much energy per charge. That's another double. And the result is that your appliance received, the heating element received 4 times the amount of electric power it was designed to deal with. and it had a life of, measured in seconds before it died. People who do the reverse, people coming from Europe to the US who use a plug adapter and shove they have less trouble. It doesn't work. It just doesn't get hot. It gets barely hot because they have dropped the voltage drop. They've reduced the voltage drop by a factor of 2. The push is only half as strong. They only get half the current flowing through it that it should. And consequently, it only gets 1/4 as the amount of power it needs. The last thing I'll do here, just because I can, is I want to show you, I'll just demonstrate, it's sort of a classic physics demonstration. It's called, I'll demonstrate Ohm's law. Do you want to do that? Yeah, I know I'll do it. I'll leave that one. I'll do a different demonstration. Short circuit. Show you. So you've all heard the idea of a short circuit, not necessarily applied properly or in a meaningful way. A short circuit, the real idea of a short circuit, is a circuit in which that looping path, literally the circuit, is abbreviated. It has a path inserted into it that cuts out certain parts, shortcuts. And the most important shortcut thing to cut out is cut out the designated consumer of electric power. So the battery is the provider of electric power. Cutting that out just makes the circuit boring. Nothing happens. The light bulb is the designated consumer of electric power. If you abbreviate the circuit so there's no light bulb in it, there's no object in the circuit that is intended to consume electric power. That's not so good, because then that battery is going to keep providing electric power, and the other stuff in the circuit is going to become consumer. Actually, the battery itself can become part of the consumer. It can get hot too. But what I'm going to insert into the circuit is just a additional piece of wire. So if I take this circuit, which is all happy and functioning nicely, and I provide a path in the circuit that skips the light bulb, watch what happens. So I'm going to I can open this up and assemble it. There we go. Okay, despite the complexity of this, all I have done is I've introduced an alternative path in the circuit that simply skips the light bulb by going through this wire. When I close the switch, current will be able to not drop off energy in the light bulb. So I'll first turn the light bulb on normally, and when I close this switch, watch what happens when current can skip the light bulb. Light bulb got dimmer. Boy, it's so powerful. Did this actually work, or I'm a little surprised that the light bulb stays full brightness. It's skipping. It is indeed. The battery has so much power that it's able to keep the light bulb going and still do this to this short circuit. Right? This is not good if it happens in your hall, in your house, right? So you don't actually want short circuits. I can turn this guy off. There are opportunities for the wiring in your house to become the consumer of electric power. And when the wiring consumes enough electric power, it'll become red hot. And your house will become red hot too. Okay. To be continued on Friday.